Lesson 1.6, we're going to be looking at a lot of two-dimensional figures. So first we're going to look at an idea called tessellation. A tessellation covers a plane with a pattern of one or more geometric shapes so that there is no overlaps or gaps. So these 5 examples here are tessellations that just use one shape to cover the entire plane. You can have different ones that you could find, but starting simple, there's some rectangles in 2 different patterns, and then we have some regular hexagons. The next one's kind of cool, the arrows pointing in different directions, but they're all congruent figures. And then that last one there, the person who created that made a bunch of leaves to do that. And there's different ways you can come up with to figure out how to come up with tessellations, an object that will tessellate. All right, we're going to have a few definitions here, and they are going to involve curves, and we're defining these because they're going to help us define some other things later on. So a curve is simply a continuous set of points, so there's no gaps or anything. So here's an example of a curve. And then the next few are specific types of curves. A closed curve is a curve that begins and ends at the same point. Now we might not know what that ending point is, but it will look closed. So this one is closed. We can see that maybe we could start here and wrap our way around. And there we have a closed curve. The beginning and ending point were the same. Next, a simple curve. It's a curve that does not intersect itself unless the starting and ending points coincide. So there's a simple curve. In fact, the first figure is also a curve, a simple curve. And then we have a simple closed curve. So a curve that is both simple and closed, which really means it doesn't have any of these. If we look back at this other figure under closed curve, it doesn't have any of these extra intersections here. So it's simple and closed. The set of points on a curve do not have to be on the same plane. They don't have to be coplanar. So if you think of maybe a string or a roll of string that's dropped and like the string gets on the couch and on the floor and on a table, that wouldn't be coplanar, but it still represents a curve. So here's an example. Classify a triangle as a curve. Now, in our everyday English language, we would say a triangle is not a curve, but does it fit the definition of curve? So so we want to see if it's just a curve, a simple curve, a closed curve, or a simple closed curve. So is it a curve? It is. It's a continuous set of points. Is it a closed curve? Yes. When drawing a triangle, it ends where it begins. Is it a simple curve? Yes. It only intersects at the starting and ending point. It doesn't have any other overlaps. So because of all those, this would be a simple closed curve. All right, circles. We're going to define circle. A circle is the set of all points that are a given distance, and that's the radius, from a given point, which we call the center, in a given plane. Now, that in a given plane part is important because if we didn't say in a given plane, it would actually represent another shape. It would be a 3-dimensional shape. Do you know what it is? It would be a sphere. So we have to say in a given plane. So here's a circle, and here's the center. So if you think about this, on the circle, all these points, this is the set of all points at an equal distance or a given distance from a given point. And that given distance is the radius, or the length of the radius. So a segment that connects a point on the circle with the center is called the radius. We're going to get to a few other ones later, but then we have the interior of a circle. This is an interesting definition, but a good definition because it explains exactly what it needs to. It's the set of all planar points, so they all still lie on the same plane, whose distance from the center is less than the length of the radius. So you would want to choose a bunch of points in here. So the radius is this long. We want things less than that long. So all these points are less than the radius. And so if you take all of those points, you have the interior of the circle, which means the points on the circle are not in the interior and they're not in the exterior. As we read here, the set of all planar points whose distance from the center is greater than the length of the radius. So those are like all these points out here that are further out than the radius. And so that blue there would represent the exterior of the circle. There's a theorem here called the Jordan curve theorem. It's similar to the idea of the postulates that have to do with separating a line into three distinct or disjoint sets, or separating a plane into three disjoint sets. So a simple closed curve divides a plane into three disjoint sets. The curve itself, so that's one, the curve, the points that are on the curve, the interior, and the exterior. So the curve itself, which was that orange, the interior and the exterior are the three disjoint sets. We'll be talking about a region. A region is the union of a simple closed curve. So the union of a simple closed curve. So we want union, so we want to include the simple closed curve and its interior. So this entire thing here would be called a region. The A and B don't have to do anything with this. And then the curve itself is called the boundary. So we might be using those terms as we work through. We have different types of shapes. We have a convex shape and a concave shape. A convex set has the property that any two of its points determine a segment contained in the set. So we're talking about the entire region here. And it's saying if we choose any 2 points, so these two above the segment here are convex. If we choose any 2 points in this set, I'm picking a random 2, and we connect those points with a segment, that entire segment still lies within our shape, within our region. And that goes for any 2 points. A concave set is a set that's not convex, or you could say 2 points can be chosen so that the segment connecting them passes through the exterior. And so just a couple examples here. We can choose 2 points that don't pass through the interior, but can we choose 2 points where if we connect them, it does go through the exterior? So if we chose this point, notice the segment does pass through the exterior, so this is a concave shape. A lot of times people think of concave as a shape that caves in. So see in this arrow, this part caves in. The convex sets don't have any cave-ins. All right, moving on. We're going to define polygon. To the right here, I have some examples of what polygons are, and then some examples of what polygons are not. And so maybe we can look at them and we would be able to tell, just fit something to that classification without a definition, but let's go ahead and define this. A polygon is a simple closed curve that consists only of segments. So that's a polygon. The side of the polygon is one of the segments that define the polygon. It's nice and simple. Vertex of a polygon is an end point of a side of a polygon, and an angle of a polygon has 2 properties, and we probably could just look at a polygon and know what this is, but here's the definition. Its vertex is a vertex of the polygon. Each side of the angle contains a side of the polygon. So it contains a vertex, and then each side contains a side of a polygon. So this angle right here is an angle of the polygon. Just want to walk through why a couple of these things aren't. Why is this one not a polygon? Well, it's not a closed curve. Why is this one not a polygon? It's not a simple curve. Why is this one and this one not a polygon. They're both simple closed curves, but they're not made only of segments. So there's different reasons why they are not polygons. Here's our different names of polygons. We know most of them. A triangle, 3 sides. Quadrilateral, got broken up there, but it's one word. Quadrilateral has 4 sides. Pentagon, 5 sides. Hexagon, 6. Hepta, 7 sides. Octagon, nonagon, decagon, and then we jump to 12, dodecagon, and then we often use n-gon if it's sides that are more than 12. We say if it had 15 sides, we could call it a 15-gon. So that n represents a number that we could throw in there. So if I ask you sometime for a hexagon, don't put a 6-gon. You need an actual hexagon. 3 terms relating to polygons on top of convex and concave. So equilateral, equiangular, and regular polygons. So equilateral, lateral meaning side, so equal sides. A polygon in which all sides have the same length, and remember we can mark segments congruent with the same tick marks. And so in this case we have an equilateral polygon, pentagon in fact, because there's 5 sides. Next is equiangular, and you see the word angle in there. That means all the angles are congruent. And that's how we mark angles congruent, and that would be an equiangular hexagon. And then the last one, the regular polygons. A regular polygon is a polygon that is both equilateral and equiangular. So the sides are all congruent to each other, and the angles are congruent to each other. Another term, diagonal. Any segment that connects 2 vertices but is not a side of the polygon. So it has to connect 2 vertices but not a side. So we could say, well, here's a vertex and here's a vertex. We connect that, but that doesn't fit the part that it's not a side. So in this case, there's a couple diagonals that can be drawn from that vertex. So there's 2. Then maybe we have from a different vertex. So we can draw diagonals from each vertex. Interior and exterior of polygons, kind of like the interior and exterior of a circle. The same idea, it doesn't have the same definition, but the intersection of the interiors of the angles, which is kind of an interesting definition, but if we take this angle and think of its interior, that would be everything over here. And then we take a different angle. So let's look at this one and do the interior of that one. If we did that to every angle, and we looked at the intersection, you would have just what's on the inside of that polygon. The exterior of a convex polygon, the union of the exteriors of the angles. So the union of the exteriors. So take all the exteriors of the angles and you have the exterior of a polygon. Realize the interior of a polygon and the exterior do not include the polygon itself. So there's the interior, there's the exterior. These are a little bit fuzzy, but here's an example. Classify each polygon by its number of sides. So that's the first thing. Then state whether it forms a concave or convex region. And lastly, if it's equilateral, equiangular, regular, or none. So let's classify them. So let's starting with this first one. Directions get covered up a little bit, but we have 1, 2, 3, 4, 5, 6, 7, 8. 8 sides, so it's an octagon. Next, it's convex. It doesn't cave in at all. And lastly, we see that all the sides are equal and all the angles are equal to each other, so it is regular. So we would say this is a regular octagon. Next one, 1, 2, 3, 4 sides, so it's a quadrilateral. It also is convex. And it doesn't have any equal sides, and it doesn't have any equal angles, so it's none. It's not equilateral, not equal angular, which means it's not regular. And this last one looks kind of like a cat, has 1, 2, 3, 4, 5, 6, 7 sides, which is a heptagon. Some call it a septagon. Looking at the side, it's concave. Caves in here, so this one's concave. And then we look at, are the sides congruent? Well, they are actually all marked, so it is equilateral. A lot of angles are congruent, but not all of them. And in fact, we have another one here that's not. And so it's not equal angular, it's just equilateral. Cool. Next. Perimeter is the distance around a closed curve. To find perimeter of a polygon, just add up the lengths of each of its sides. If it's a regular polygon, and remember regular has an important term to it, or meaning, it's not just plain polygon. Or regular polygon means it's equal angular and equilateral. But a regular polygon, the perimeter is the number of sides times the length of each side. So find the perimeter of each polygon. Well, this triangle has 3 lengths. We add those up, 10 plus 8 plus 4. 10 plus 8 is 18 plus 4 is 22, so this is 22 centimeters. This one, they're all 9, and there's 5 of them. Oops, I forgot to change the names of each of these vertices. They shouldn't all say A. But we can do the perimeter equals the number of sides times the length of each side is 45. And no units are given, so we can just write units. This was supposed to be like A, B, C, D, and E. So polygons we can name by their vertices. So we could have called this pentagon, A, B, C, D, E. You always want to list in order. You don't want to do A, C, E, D, B. They always have to have consecutive angles, so this is a no-no. Back to our circle definition. These are a bunch of the ones that we named before, these definitions. There's a few more that we want to mention now. They are a chord. A chord is a segment having both endpoints on a circle, so there's a chord. And then there's some special types of chords. There's a chord that passes through the center, and that is called a diameter. So there's a diameter. And the last one we'll mention for today is an arc, and that is a curve, so a continuous set of points. That's a subset of a circle. So remember, the circle is only this darker orange part, the points that go around, not the interior, not the exterior. So if we just take a subset, a curve, that's a subset. So it has to be continuous set of points and then a subset of the circle. And we talked about interior and exterior already. Here's just some ways of how we name things. We name a circle by its center, center M, or the font got messed up here. You can just put a circle M. So that symbol, something went wrong with that, but circle M. A center is named by a point, so we just say point M is the center. M is the center of circle M. A radius, well, a radius is a segment, so name it that way. So we can say, in this case, we have a radius MK. The segment's supposed to be right over the M and K. A chord is also a segment, so you name it as a segment. So segment NT is a chord. And then a diameter, also a segment, so QR. And then arc. The way we name an arc is we put a little arc over top of the beginning and ending of the arc. I know you can't see that L up there right now, but that is point L right there. So arc LK. There's some different measurements that are important within a circle. First of all, the diameter is equal to 2 times the radius. That makes sense. The circumference, well, first of all, we need to define it's the distance around the circle, or we could say the perimeter of a circle. There's a term pi, which you've heard of, and there's the symbol for it. It's a Greek letter. Pi is equal to, this is the definition of pi, it's the circle's circumference, the ratio of the circle's circumference to its diameter. It's always the same, and it's equal to pi. So you could have a huge circle, find the distance around it, divided by the diameter, or you could just do a little circle, kind of like this one down here. We could take the circumference divided by the diameter. You will always get this number pi. Usually we use 3.14, or if you're doing fractions, 22/7 is accepted as a good estimation for pi. And we have, it's really just solving this equation for circumference. Circumference is pi times diameter, or let's just write the whole thing up here. Circumference is 2 pi r. Make sure you know that formula. And we are going to use it here. Find the missing measure. Well, we don't know the radius. Well, we know circumference from before at the bottom here. Circumference equals 2 times pi times the radius. So we use that formula. We're going to plug in the circumference, which is 10. And then we can divide both sides by 2 pi. And then we can figure that out. So be careful. I want to show you how we do this on our calculator. Do not do, so I'm showing you what's wrong, 10 divided by 2 pi. This will give us the wrong answer because your calculators do the order of operations. So this will do 10 divided by 2 and then multiply that answer by pi. And it says it's 15, which doesn't make sense at all that the radius would be more than the circumference. So make sure it's 10 divided by, and we have these parentheses, divided by 2 pi. And so now it's multiplying 2 times pi first, and then 10 divided by that, and that will give us 1.59, which is the radius. 1.59 centimeters. And then it says, find the circumference of a water tower that measures 60 feet across. Well, 60 feet across would represent the diameter. So we know the diameter, and so we can think, oh, well, circumference equals pi times diameter. We can plug in 60 feet for the diameter. We can multiply that out. So we want 60 times pi. And we get 188, about 0.5, 188.5 feet. And so that's using that formula. So I know there was a lot in that lesson, a lot of different terms. You have a bit of a longer assignment, but it is a lot about terms, so you can work on that. And there is the assignment. Have a great day.